If you're kind of new to SolarEdge, or if you haven't been using SolarEdge for a while, we are a public company. We are traded on NASDAQ under SEDG. We had our earnings call earlier in the week. So rather than putting up our normal numbers slide, I'm giving you the earnings call slide. These are kind of the highlights for us for Q1 of 2017. As you know, the market has been a little slow to develop in Q1. Everyone's kind of in the same boat where we're all trying to navigate our way through. These are the numbers that we put up. Pretty good numbers overall. If you want to know more information, just go onto our webpage, look up investor relations, and you can get these slides and do a little bit of research. I do recommend for any of the public companies that you're purchasing product from, do a little bit of research, understand where they are financially. It's just good practice for you to do that on a regular basis. There we go. Oh, let me go back. So it is working now. It is a bit of a lag, though. All right, SolarEdge, we like to say it's as easy as 1, 2, 3. We have our inverter, which is on the ground level. We have an optimizer on the rooftop level, and we have a cloud-based monitoring platform. The inverter is pretty common in the industry to see one of these on the side of a house. You can also think of it as a combiner, as a rapid shutdown controller, and as a central hub for communications. So even if you're doing kind of a microinverter type application and you're putting everything on the rooftop, usually you still have a ground-based communications hub. You have a ground-based combiner for the larger system. So if you're new to SolarEdge and you're coming from microinverters, this inverter is going to be a lot like putting that box on the wall that you put now for communications and combining. It just does the inversion for you. If you're installing string inverters, this is going to be very, very similar. On the power optimizer side, now this is where the rapid shutdown piece comes in. We're controlling the modules at the module level. And in commercial systems, as you'll see, we're controlling 2 modules to 1 power optimizer. So that's going to give us the ability to control the voltage on the rooftop. And that's how we're going to meet rapid shutdown. We do have the cloud-based monitoring portal, which we won't go into today. We do have a couple webinars that I'll talk about at the end and kind of give you our schedule of webinars for the next month. And you can learn about rapid shutdown, learn about the monitoring platform in detail there. On the residential side, we've introduced our HD Wave inverter. Right now, that power class is 3 and 3.8 kilowatts. We are rolling out the 5 kilowatt very soon. Anything larger from 5 kilowatt all the way up to 11.4 will be done on our standard single-phase inverter platform. On the commercial side, we have 208 volt and 480 volt solutions. So on the 208 side, we have a 9 kilowatt and a 14.4 kilowatt inverter. On the 480, we have a 10, 20, and our most popular product is a 33.3 kilowatt inverter, and that's all 480 volt. Let me now introduce Jason. We'll get right into rapid shutdown. So Jason Bobrook is our Director of Code Compliance. He's our expert of all things code. He's talking to the code experts. He's talking to the utilities. He's kind of got a Rolodex that is different than the Rolodex that most of us have in the company. So he's a great resource for you. If you have any questions on code compliance, please feel free to. He's going to be your expert for the next 45 to 50 minutes. And Jason, I'll turn it over to you.
Thanks, Mike. Good morning, everyone. Do I have control now? Okay, great.
Looks like it to me.
Okay, well, I'll start with a brief history. I realize we may have some folks in the audience that are new to rapid shutdown. We'll talk about the code itself, and then we'll get into the details of how the SolarEdge products work. And then hopefully we'll have a fruitful question and answer session. We always get a lot of nice discussion, and that's really my favorite part. So I'd like to leave time for that. So just a quick summary. Rapid shutdown, the whole concept of rapid shutdown was driven by emergency responders and the PV industry in an effort to create a safer environment for emergency responders to perform their basic operations that they would do on a rooftop without a PV system. And so as soon as you put a PV system up there, this presented some challenges. About 80% of the firefighting community is volunteers with basic electrical training. They're trained on how to save lives, not necessarily on how to wire up a PV system or install panels or disconnects or things like that. So there's not as much familiarity with the system as there may be in this audience. Those of us that have been installing PV or working for manufacturers that make PV system components or for years are all very familiar with it. So there's one basic need. The emergency responder needs to get to the roof. They need to ventilate the roof so that they can relieve the room below of superheated gases and smoke. This is a way to provide oxygen to occupants. It's also a way to control the way that a fire may spread. And so that's part of the normal operations. They'll look at the roof, they'll look at the structure, they'll decide, where do I need to ventilate? As most of you know, we want to put PV systems on roofs in the industry, and a lot of people want to put pretty big PV systems on the roof. So this covers a lot of the roof real estate that they would normally access. And so the real need was to describe what the hazard is and then give a method on how to control the hazard. And the other thing that's confusing, last but definitely not least, is you have a DC disconnect, you turn it off. When the sun is shining, the conductors are still energized because of the sunshine and the PV module being the source. So then along comes NEC 2014 with several changes, the biggest one being rapid shutdown. The key is this just allows emergency responders to perform their normal operations with a limited risk of shock. And I like to use the word limited risk of shock versus safer operations or things like this, because that's what rapid shutdown does. It just limits the hazard. Doesn't completely eliminate it. So I talked to a few people in both the code making panel and in the firefighting community, and I wanted to get the history of what was the original intent of the code. And I put this up here because this kind of will bring us back to why we did all this in the past. What it is now is a different animal, and we'll talk about that. But the original intent was to reduce the area of the energized conductors in an emergency, to have something you can initiate, the flip of a switch, the push of a button, or perhaps it's automatic when somebody pulls the meter on the house, or loss of grid. And then the other idea was, let's reduce the voltage in the entire home run from the array. Pedaling back a few years, people weren't really so much thinking about what's happening within the array. We just wanted to make sure that the home run conductors leaving the array were safe in case somebody was ventilating a roof and they needed to cut through a conduit, or by accident they did that. So. All right, so where are we today? So this is a slide I like to show. I'm very thankful to the folks at the Electrical Code Coalition. They make these nice charts and keep them updated. It's a great website. I do encourage people to go there to look at kind of the national view of which states are using which versions of the code. I mean, the one thing that's clear when you just look at the colors is NEC 2014 is a dominant code. And I don't think that's news to anybody. But what's interesting, if we move to the right, you see that a lot of states are in transition right now. So to kind of decode it, if a state has a color that's orange or blue, it's in a transition period. So if it's grayed out, then there's really nothing happening right now. But I think what's important to note is a lot of the states that are colored in red on the left are also in transition on the right. And so not only do we have NEC being the dominant code right now, we have a lot of states that are using NEC 2014 that are evolving or starting to adopt NEC 2017. So I just grabbed some dates These dates are sometimes flexible. There may be an announcement, a planned target date, but they may not hit it. I just thought it was interesting to show. So the first dates we'll look at, these are dates where states that are not on 2014 will soon adopt NEC 2014. And Hawaii just adopted. There's a few announcements out about that. We see Louisiana and we see Florida will be coming online this year. Yeah, apologize for the noise there. An airplane flying over. So about three states are really moving to the 2014 code. But what's interesting to notice, how many states are moving to the NEC 2017 code? I counted about 15. So I'll drop those dates in. A lot of that is happening in July, like August and September are popular dates, and then some things happening at the end of the year. And so to me, this was actually kind of eye-opening. I hadn't been to the website in about a month or two, and to see just how many people are transitioning to 2017. So it becomes more important when we talk about rapid shutdown, because the rules have definitely changed in the 2017 code cycle. Okay, now we'll jump right into what rapid shutdown means and then how the products work. So there's a section in the PV section, 690, and it's 690.12. It requires rapid shutdown to de-energize the conductors. It's less than 30 volts within 10 seconds. That was the original NEC 2014. Currently been modified through a tentative interim amendment to 30 seconds. So basically, it does the same thing. You have a little bit longer. You don't have to do it in exactly 10 seconds. You have some more time. Key takeaway is that this can add cost to PV systems. Traditional systems that don't have a built-in rapid shutdown function, you'll have to add something. And so it's important. So looking at the slide, what we're seeing here is just a quick illustration of what the SolarEdge rapid shutdown looks like. I'll get into it in more detail about what that 1 volt means. But essentially, when the inverter is initiated for rapid shutdown, each optimizer will go to about 1 volt, and we'll talk about how that works later. Before we get too much into the products, I just wanted to review the code quickly, because we'll be talking about the section of the code. I've got NEC 2014 up here because it's still the dominant code, and this is the text just copied right out of the book. So I'll jump through it real quick for those who aren't familiar with it. I think the first takeaway is it's for PV systems on buildings. It's not ground mount systems. It's not carports. Some people may argue that, but it depends on if you want to call a carport a building. But for the most part, it's for dwellings, buildings where you have occupants and where firefighters will have a need to ventilate the roof, either to save lives or to save property, if you think of an inventory warehouse or something like that. Step 1 says the requirements for controlled conductors shall apply to PV system conductors, and so only PV system conductors. And then you have some restriction on the length of those conductors. So a little bit of confusion here, and it was clarified, I think, in the newer code version, but it says 5 feet in length inside the building. So I'm talking about the length of the conductor there, not how far away it is from the penetration, or more than 10 feet from the PV array. So the second part has nothing to do with the length of the conductor, it's the distance from the array. And so this is really a combination of how the system's installed, what technology you use. So I put installer plus SolarEdge as the solution provider. We do that with the module level optimizers. The second part now gives us some criteria. The control conductor shall be limited to not more than 30 volts, 240 volt amperes within 30 seconds of rapid shutdown initiation. So thinking back to the original intent, it was limit the energy that an emergency responder could be exposed to. So that's exactly what this does. You're limiting the voltage, you're limiting the overall volt amps, which is energy, and then that has to be done in a specific time frame. So it needs to happen quickly so that emergency responders can then perform their operations. Number 3 gives us a way to measure that. So how the heck do I measure this? It's spelled out pretty simply. Just take your measurement on voltage and power between any 2 conductors or any conductor and ground. This is, pretty much the technology solution. So the solution provider there is SolarEdge, and we'll talk about the system conductors in a minute. And you can see what the voltages are in the diagram that I have. Number 4 says the initiation method shall be labeled. So you've got to put a sign on the system. The emergency responder needs to know that there's a rapid shutdown system. There's some rules for that. Last but not least, perhaps one of the most misinterpreted parts of the code is equipment that performs rapid shutdown shall be listed and identified. And so this means the products that are used for rapid shutdown need to be listed products. And so we do have listed products. All of our equipment is listed. And today, in fact, all of our equipment has been evaluated and listed for rapid shutdown, which is not a published standard, by the way. There is a draft, and that's what people are doing that want to meet the NEC 2017 code. We'll get into that a little bit more. I'm sure we'll have questions on that. What is a TIA, tentative interim amendment? The mechanism of a TIA is to allow a change quickly without waiting for a new code cycle. It can be submitted, voted on, approved, and implemented very, very quickly. It can be used for emergency nature type revisions. This TIA was issued on August 4th and became effective on the 24th of 2016. Basically just says you have 30 seconds now instead of 10. If you'd like to look it up, you can find this on the NFPA website. And there's many other TIAs to the 2014 code as well. This is the one we're going to talk about today. Oh, we're not quite done with code yet, but I thought I would try to make a diagram that is simple. So it does a few things. The purpose of this slide is so that people can quickly visually compare the NEC 2017 requirements with the NEC 2014 requirements. So I'll talk about the diagram first, and then we'll talk a little bit about the points on the left. So I'm pretty sure that everybody's familiar with NEC 2014. That's the half of the roof that's on the left. I know my borders don't really make sense, but if you think of this being a three-dimensional picture, then they do. And in fact, that's an important point. The code only says 10 feet from the array. It doesn't tell you which direction. So you can consider that a three-dimensional bound, if you will. Anything within that 10-foot boundary can be at 600 volts. It could be at 1,000 volts if it's a commercial system. The conductor that is 5 feet in length, inside the building, could be at that hazardous voltage. So I've colored that red on the left. And then the controlled conductors in the system are colored in green. So once rapid shutdown is initiated, then you see the green conductors would be at the controlled voltages and currents. Now, just visually looking to the right, you can see a few things that have happened. I think the most obvious thing is the border has decreased. And so now the language says 1 foot. The boundary is defined as 1 foot from the PV array in all directions. That's a much smaller boundary. We decreased it by 90%. The other thing you notice is the color of the conductors. The conductors now within the array can be controlled to meet the code, and they can be controlled to less than 80 volts. I drew that yellow instead of green because there's still some, there's still some arguments in the industry as what is a safe voltage. It's again, the original intent of the code is to reduce the electrical hazard. And so I think it's easy to argue that a controlled voltage at less than 600 volts is definitely a reduction in a hazard. The other thing that's interesting is you now have 3 feet inside the building once you penetrate, and it's no longer based on the length of the conductor, it's based on the distance from the point of penetration. So that's why you see a little half circle, hemisphere, I guess, if you're thinking 3 dimensions. Everything outside of all those red dotted lines is now the controlled conductors. So in a nutshell, that's what you get with NEC 2017. And obviously the time has increased, but you know, we're consistent with the TIA now, so it's not as big a change anymore. And I summarized on the left. You know, here's all of the main bullets. I didn't want to go through the whole section in detail. There's a lot of it. The other thing I think that's up here I didn't talk about yet was the initiation devices are more defined. So in 2017, it's now defined that you can have up to 6 initiators. Grouping is defined. The location of the initiator is defined. It needs to be outdoors. That wasn't spelled out in 2014. Equipment certification has increased. Instead of simply using equipment that's listed, you have to use equipment that's listed for providing rapid shutdown. That means you have to take your rapid shutdown solution, go to a NERDL, which is a nationally recognized testing laboratory, and have that system or that piece of equipment evaluated as a PV rapid shutdown system. Another option is PV rapid shutdown equipment. We can talk about those discrepancies if we need to. There's more signs required. There's different ways to comply. NEC actually allows 3 different ways to comply for a system. We're talking about inside the border. You can get all that stuff inside the border listed as a rapid shutdown array by a NERDL. It's hard to do that today because there's no standard in existence, but there is one being written. You could use module level power electronics like optimizers to simply control those conductors to a state that's less than 80 volts. Or you could use a building integrated photovoltaic product that doesn't have any exposed metal. And so those are 3 ways to comply. Today, what's really available to the market are the last 2. So we have module level power electronics such as DC optimizers or microinverters or other DC to DC devices with a switch in them perhaps. And we have a couple of BIPV products on the market. Those are readily available. Try to go out and find a rapid shutdown listed array to a standard. I don't think there's one out there yet. Somebody please let me know if there is. But maybe we'll start to see some of that stuff in the future. But that's a whole nother effort, and it's pretty complicated when you start getting into listing all the nuances within an entire array assembly. Okay, so enough code there. Talk about the SolarEdge solution. So SolarEdge has traditionally had a system that was designed for safe installation and maintenance. This is part of the product, mission from the beginning, I'll call it. So the idea really was have remote monitoring instead of diagnostics at the workplace on the roof. This means you can go into the monitoring portal and look at the optimizers and see what the module performance is. You have a nice graphical layout of the array. You can pinpoint issues on the roof without actually having to go to the roof. At some point, you may need to go to the roof, but this allows you to at least do some troubleshooting beforehand. With that, we coined something called Safe DC technology. And all Safe DC is it's a way to reduce the voltage on the PV optimizer so that the conductors between the PV optimizer and the inverter can be at a very low safe voltage. And so we simply just turn the voltage down the optimizer to 1 volt. And that's when you put the thing in Safe DC mode, you get 1 volt per optimizer. So what Safe DC gives you get no high voltage during installation or maintenance. When the inverter is turned off or disconnected, even without rapid shutdown, they go to a Safe DC state. And this has been there for some time. We also have the integrated arc fault protection. And today, in many of our products, we have integrated automatic rapid shutdown. And I'll talk about what automatic means across the product line in a minute. That automatic rapid shutdown meets both NEC 2014 and 2017. So back to the Safe DC solution. If you want to know the voltage in the string, you simply just add up the number of optimizers in the system. Actually, this graphic says modules. So the assumption here is there's one optimizer per module. So you add up the number of modules, you've got your voltage. On to the next slide. How does that work? You only need to remember that if you're working with a three-phase commercial system, many times customers will want to use a 2-to-1 configuration. So there will be 2 modules connected to one optimizer. So in that case, your safe DC voltage would be the number of optimizers, not necessarily the number of modules. So how does all this relate to rapid shutdown? You may be asking, I came to this webinar to learn about rapid shutdown, not about safe DC. Well, safe DC, or I should say rapid shutdown for our products is really just a small modification of our already existing safe DC function. So I put a table up here. We look at the controlled conductors. I think that's pretty obvious how that works. Going down to the timing row, the safe DC typically took anywhere from 60 seconds to 180 seconds. And so this was dependent on the size of the string, the type of optimizer, the inverter model. You could turn everything off. It would just take a minute and a half, maybe, for the DC string to completely de-energize. In 2014, it says you had to do this in under 10 seconds. Now it's 30 seconds. So that was a big difference. So we did have to do a modification to the safe DC system to make it compliant with rapid shutdown. Let's see, everything else down to the listing, everything was NERDL evaluated and listed from the beginning, third-party testing. We continued that through product inception to today. The initiation, let's talk about the methods of initiation. So this is always a fun topic. We have a lot of different ways to initiate safe DC. A ground fault will put the system in a safe DC. Loss of AC power, turning off the DC safety switch. There's also an inverter on-off switch, the little red switch that's on the body of the inverter. You can do it remotely with an RS-45 signal or a SunSpec Modbus control. And it can also be done remote via the web if the inverter is tied into the monitoring system and it has some active control capability. So what is different about code? In NEC 2014, it didn't really tell us how to activate rapid shutdown. In NEC 2017, it's much more specific. So it talks about the disconnects, the types of disconnects, outdoor location. And we can definitely meet that in a variety of ways. It's really up to the system designer to choose what's most convenient. So safe DC versus rapid shutdown. This is a slide that Mike made. I like it a lot. It just gives you a quick view of the differences of the systems. So just moving from left to right, we have kind of traditional system. In the middle, NEC 2014, you still had some high voltage within the array. And if you look at NEC 2014/17 rapid shutdown with safe DC, which is our product, then you have controlled conductors within the array. And so you could kind of see the evolution. All right, now you're asking exactly does this stuff work? I've been telling you, I'm going to tell you how it works. So here's the nice slide. This is a mock-up system in the PowerPoint. It shows an array with PV modules and DC optimizers. Get my mouse up here. Obviously, the PV module, there's one optimizer per PV module. Those are connected in series to form a string. We have the inverter on the left. And what I'll do now is put it into an on state graphically, if you will. Modules producing power. The maximum power point tracking is performed at the DC optimizer. The DC optimizers will control the DC bus. So the bus voltage is typically around 350 volts on residential. In order to achieve that, each optimizer will regulate at about 22 volts in this scenario. So you start to add up 22 volts in series. And you can see pretty quickly you get to a hazardous voltage. Even just with 2 optimizers, you're above the limit of 30 volts. And so definitely the home run, going back to the inverter, is at a higher voltage, hazardous voltage. So system's on. Now we're going to activate rapid shutdown. And how do we do that? Well, we place it into the safe DC mode. So safe DC is active. We'll say in this example, somebody turned the rotary disconnect. That would be one way to do it on this model. On the automatic model, that could be done by just turning the PV breaker, which would kill the AC going to the inverter and trigger it to go in a rapid shutdown. That's on certain models that have automatic rapid shutdown. And then we could do it remotely via communications or fire alarm system, etc. So what happens in a rapid shutdown state? The optimizer quickly moves the maximum power point tracking so that the power output is 0. So really 0 currents. There's really nothing we can do about the VOC of the module. Those cells are going to produce voltage when they're illuminated. So the module will remain at 40 volts VOC. The optimizer will then output 1 volt DC. Why do we have 1 volt DC? Well, we need to maintain communications with the optimizer, and so that allows our communication signal to exist. We chose 1 volt DC because it's convenient when you're troubleshooting. In safe DC mode, you can count the number of optimizers that are activated simply by just looking at the voltage with the voltmeter. And so what actually happened that made this occur? So what was the trigger? It's probably what you're asking. Upon activation of safe DC, the communications signal that's provided to the optimizer was turned off. And so I think of that as a keep alive signal. Some people call it a heartbeat signal. So the inverter and the optimizer are constantly pinging each other saying, hey, I'm here, I'm here. You take that signal away, the optimizer says, oh gosh, the inverter's gone, I need to be in safe DC mode, or a connector's been compromised, or somebody's cut a wire, or a number of reasons, go into safe DC mode. So that's what we did. We just take the signal away, and the optimizer reverts to a safe state. So once you add up all these 1 volt signals, you have about 16 volts on the home run string. And that fits the requirement of being less than 30 volts. So the system's compliant with a rapid shutdown. We'll talk a little bit about the product. So the single phase inverter, this is our flagship inverter right now. It's used quite widely in North America. People are probably very familiar with these. It does have compliance to NEC 2014 and 2017. So the device has been listed for rapid shutdown and evaluated by a NERDL. On this model, it's important to note that we have initiation that is manual. So to initiate rapid shutdown today with this model, you have to turn the DC disconnect, which is this rotary switch here. That puts everything in rapid shutdown mode, and just like we showed in the example. Oh, I have a table. Great. So the only model that has what we're calling automatic rapid shutdown, where you don't have to turn the safety switch, is our new HD Wave model. And so that's not what's pictured here. We'll show that next. Just a quick view of the model numbers. The key takeaway is the models today are followed by an A. So you'll have like the SE7600A. The new HD Wave inverters will be followed by an H. So for example, SE3800H. And that's one way to tell in single phase the difference between automatic and manual rapid shutdown. We do get a lot of questions about how this works in a storage system. So I thought it would be important to go over a storage system briefly and talk about how rapid shutdown works. So storage has a lot more components than a typical PV system. Obviously, there's the battery pack, the transformer. You may have a backup loads panel. it's shown here. And typically, when somebody is putting in a storage system, they want backup power too. So they do a backup loads panel, and the system by design will remain energized when the grid goes down. So we'll switch into backup mode. The PV system will still be active. The backup loads panel will be supplied with electricity, and so you still have a system running. So what do you need to do? To activate rapid shutdown, you simply need to be sure to turn the rotary switch on the inverter. So the inverter knows, hey, this is a situation where we need to go into rapid shutdown. I'm doing my normal backup thing. There's no other way it's going to know. So don't expect an automatic rapid shutdown behavior with the SolarEdge system. It has to be manually activated today. And how do you tell? So you'll see that we have a couple of different label strategies here. Some of this is because the product is evolving. So in general, things that were pre 2017 will have a label that looks like the lower label, and it will be on the DC safety switch. So for folks on the phone that aren't familiar with the architecture, the upper portion is technically the inverter. The lower portion is a disconnect enclosure or DC safety switch, if you will. Those two pieces come pre-assembled from the factory. They have their own labels. So the DC safety switch will be labeled with integrated rapid shutdown. Some of the newer, well, I shouldn't say newer, but since 2017, inverters will be coming out with additional labeling to meet the code, which will say photovoltaic rapid shutdown system. You may see this label on the DC disconnect enclosure. You may also see it on the inverter in some cases. Okay, so we just talked about that product line. Our new product line that seems to be very successful and very popular these days is the HD Wave. So it's smaller, lighter, more efficient. You can oversize the DC strings. Just a lot of things have been optimized. Displays cleaner, the buttons are really slick. So there's less heat. It's got improved components. We've gone to high reliable thin film capacitors that are smaller than the traditional bulk electrolytic capacitors. You can get built-in revenue grade metering. And last but definitely not least, you can get integrated auto rapid shutdown. So what is auto rapid shutdown? So since we came out with a new product line, we took the opportunity to take away the need to turn the rotary disconnect. So with the HD Wave version, you can simply turn off the PV system disconnect, which would be an AC disconnect. In many cases, you can use the breaker as the means of disconnect. So that could be the rapid shutdown initiator. Either way, you need to label that initiator, but it just makes it happen a lot easier than having to go over to the inverter and turn the rotary disconnect. So. Oh, here's my slide on automatic rapid shutdown. Great. So and the nice thing about automatic rapid shutdown is since you're turning the PV system disconnect off, the AC conductors are controlled in under 2 seconds by the nature of the inverter. The DC conductors are controlled in less than 30 seconds. And so you've got all of those conductors controlled to meet the code. Today, that's available in 2 main model lines. It's available only in the HD Wave series single phase. And it's available in 3-phase models, but only 2 models, the 14.4 and the 33K. And you may be asking yourself, why isn't it available in all the models? I want it in everything. We had to go through a transition to implement the automatic rapid shutdown, and we just simply weren't able to go back and add that feature to every product in the product line. Moving forward, as new models come out, we'll be transitioning to only automatic rapid shutdown. But today we have some mixed product lines. So I try to map that out in a table here so folks know what to get. The important thing is talk to your local sales rep. understand which model you're designing with and what you need to do to make it rapid shutdown compliant. And so, for example, on the 9, 10, and 20K US three-phase versions, you do need to have a rapid shutdown kit. So I've listed the part number of the kit. That kit would need to be ordered and placed in the DC disconnect for the system to be compliant. About a month ago, we started shipping inverters with that kit installed at the factory. However, many of those inverters may not have hit the market yet or hit job sites yet. They may be in a container or in a distributor's warehouse, who knows. So it's very important to identify the vintage of the inverter that you have and understand if you need to install that kit or not. Which models have automatic rapid shutdown? Well, the 14.4 and the 33 both have automatic rapid shutdown. However, there still are some legacy models out there. I'm not sure if I know the exact cutoff date. It was a while back. Again, talk to your local sales representative and understand if you have one of the legacy inverters, you will need to get a different kit. And that's detailed here in this table. So important slide. You don't have to memorize all these part numbers or anything. Just talk to your sales folks and they'll be able to help you out. Okay, the products are listed. Standard is UL 1741. That's the base standard for inverters. 1741 has a lot of new sections that are being written. So it's expect that there will be additions to UL 1741 in the near term that will cover rapid shutdown listed PV systems and whatnot. So there is a change in the requirement in the code. I put the text up here so people can see the difference side by side. In 2014, it says equipment that performs the rapid shutdown shall be listed and identified. That's interpreted different ways by different people in the industry. I think in NEC 2017, it's much clearer. It says equipment that performs the rapid shutdown shall be listed for providing rapid shutdown protection. So that's very clear. It says that the equipment needs to be evaluated by the NERL. Software settings, last but not least, be sure that the rapid shutdown function is enabled on the inverter. Most inverters, I'll say, so upwards of probably 80% of inverters that are out there today will already have this set in the menu to default to a rapid shutdown enabled state. However, like any product line, there are some legacy products still out there in the market today. Some of those legacy products shipped with rapid shutdown disabled because it wasn't a required feature yet in many markets. So you just want to check just to be sure. Go through the menu before inspection. Make sure that the system is set for rapid shutdown. It's pretty simple. It's through the maintenance menu. Okay, what else is required? A labeling. Probably no need to spend a lot of time going in depth here. You have to label a rapid shutdown system. NEC has a section that tells you what the label must look like, tells you about the letters, the color, etc. That's in section 56. There's a bit of a change in the labeling in NEC 2017 versus 2014. The labels are much more specific, and for good reason. There's a need to define how the system complies for emergency responders, because there's a clear difference between NEC 2014 and NEC 2017 on the controlled voltage within the array boundary. So the signs required will inform the emergency responder what type of system is on the roof. So on the left, You can see for a standard type PV system, a string level, rapid shutdown, the signs in first, it's in red, and it says the turn off rapid shutdown switch to shut down the conductors outside the array. Conductors within the array may remain energized, or doesn't say may, but energized in sunlight. Big difference on the right is the signs in yellow. It still tells you how to turn off the switch to initiate rapid shutdown, but it also says that there's reduced shock hazard within the array. So this gives a little more confidence to the emergency responder if he needs to perform any operations right next to the array. It's really within the boundary. This doesn't mean that somebody is going to take a chainsaw through a PV module. I mean, I think that's sometimes a misinterpretation. I've talked with a lot of emergency responders. They do not want to cut through PV modules. But what this lets them do is they know they can get much closer to the PV module, to the array. There's a 1 foot boundary. And even within that 1 foot boundary, the conductors will be controlled. So it just gives a little more flexibility. If somebody needs to remove part of a PV system, that can be done in a more confident way. I put the slide up here because we do get some questions about the AC side of rapid shutdown. And this is an important thing to talk about because there still is some confusion, I think, in the industry, even among the code making panel. So this is one of the key points of conversation right now as we're discussing the NEC 2020 code cycle. So what is a PV system conductor is the real question. Code says it has to apply to PV system conductors. So is this just the DC conductors on the rooftop? Is it the AC circuit coming from the main distribution panel? Does it start at the inverter and then go to the roof? Is it the PV system disconnect? NEC 2017 clarifies that in the definitions of a PV system. It talks about the PV system disconnect being the point where the PV system conductors begin. So what does that mean for rapid shutdown? There's a lot of discussion about this, but most inverters in the market today, in order to comply with anti-islanding, will disconnect from the grid upon loss of AC power. They don't always disconnect. The term that's used by IEEE is cease to energize. So an inverter can cease to energize, which means it's not pushing energy back to the grid, but there still may be voltage on the terminals. In our case, we actually disconnect from the grid. We have an internal relay. So as soon as there's loss of AC power, in under 2 seconds, the inverter ceases to energize that circuit. It's important to know, though, if that circuit could still be energized by the main distribution panel. So you could have a live AC circuit even when the inverter's off. The way to get around that is with automatic rapid shutdown, simply just turn off the breaker, pull the meter, turn off the PV disconnect. That's going to de-energize those lines from both sources. So the main distribution panel can't energize the AC circuit anymore because the disconnect's open. The inverter is going to turn off. It's not going to energize those conductors. So those AC conductors are going to meet the rapid shutdown requirement with SolarEdge equipment. All right, so passing rapid shutdown inspection. I've put these bullet points. It's useful for folks that are doing this for the first time. Read the manual. We give some good instructions in there on how to install everything. Be sure rapid shutdown is enabled, as we talked about. Pre-test the system. It's not a bad idea at all. I need to modify this sentence. Monitoring the voltage on the LCD screen is really not recommended anymore. We recommend a voltmeter. Sorry, I didn't modify this yet. But yeah, pre-test the system, put a voltmeter on the DC conductors, turn off the disconnect, turn off the rotary switch, whatever method you're using. See what happens on those conductors, because that's really what the inspector wants to look at sometimes. It may be tested at final inspection. We're seeing this a lot in new regions where NEC 2014 has recently been adopted. California is a great example. We're getting a lot of feedback from installers and inspectors in California that are going through this for the first time. Once you go through it, it's pretty simple. It's easy to keep going. But call me if you have questions. Contact us before the final inspection. It's another nice bullet point. It's a lot easier to take care of any issues that could be happening beforehand. And then last but not least, when you're going through plan check and permitting, be sure rapid shutdown devices and locations are shown on the drawings. We've had several cases where a customer may call us up and say, I can't get the system through plan check. It's not going to make it. You guys said you had rapid shutdown. And it's okay. Well, let's look at your documents. Nowhere on the documents have they indicated anything about rapid shutdown. There may be a SolarEdge data sheet in the back with the PV module data sheet. The plan checkers don't know necessarily that this system is going to have rapid shutdown. So it's good to show the location of the initiator, the location of the signs. You can call out, you can put extra labeling on those documents. Just make it easy for the plan checkers because they're not used to rapid shutdown systems yet either in regions they're just adopting NEC 2014. All right, lessons learned. So firefighters and HJs, they definitely recognize the value of shutdown and safe DC. We do get a lot of feedback from the industry. It's positive feedback. We like what we're doing. We believe this is the best way to control the conductors. Auto rapid shutdown can be confusing, and this comes from a lot of different interpretation of the code. It's definitely not code specific. So nowhere in NEC 2017 or 2014 does it say you have to use automatic AC initiated rapid shutdown. Issues with third-party solutions, we do get feedback from things that commonly aren't working, or somebody trying to apply a third-party solution to our system. The key is it's built in. You don't have to add anything. It's there. We hear some feedback about fusing, current ratings on different combiner boxes. Sometimes communications can be challenging, low voltage wiring. If you have communications going to a roof via some low voltage wiring network, these things need to be troubleshot. Being ready for NEC 2017, that would mean controlling conductors within the array. It's complicated. It's much simpler, at least that's our view. It's much simpler to go with something that's integrated and built in to the equipment. Commercial strings and inverters mounted on the array. Now this is an interesting one. So a lot of commercial sites, in order to meet NEC 2014, simply put the inverter near the array on a rooftop on commercial sites. Within that 10-foot boundary, you could claim that if you go throw the AC breaker, the AC lines would be de-energized. They would be outside of the boundary and meet rapid shutdown. The inverter and the DC conductors within the boundary would still be at a hazardous voltage, but that's okay because you have a 10-foot border. That practice is now being challenged in some areas simply because of the wording in the standard, which says products must be listed for providing rapid shutdown protection. So if you're to take that strategy on a commercial roof for an NEC 2017 application, you could conceivably try to put the inverter within 1 foot of the array, maybe tuck it up under a tilted system, and the inverter could be within the boundary. The question that's coming from inspectors is that inverter, has it been listed for providing rapid shutdown protection? And so that's still open for debate in many regions. Check with your local AHJ about re-roofing or replacing PV systems. We have heard, and I think this one specific case I'm thinking of came from California, that if you have a pre-NEC 2014 system and you have to re-roof, you take off the PV system, at least the modules, re-roof, and then put the modules back up. Some jurisdictions may make you bring that PV system up to code. And so up to code would mean you now need to add a rapid shutdown system if you don't already have one. So if you have a SolarEdge system, it's not a problem. It's already compliant. You take it off, re-roof, put it back on. But just be aware that that might check with your local city and inspector and understand what's required if you're going to do a re-roof. All right, we're coming to the end of the presentation. A couple of resources here that I encourage people to use that are online. We have a video to demonstrate how to measure rapid shutdown compliance. And so Mike does a great job here with a voltmeter and a stopwatch. There's a really good article by IAEI magazine, talks about rapid shutdown. It's by Mr. Bill Brooks and Jim Rogers. And there's a very good article in Solar Pro as well. Same author there. I encourage people to read these. These guys go into detail. They have great diagrams. They were instrumental in getting the code modified in the first place, and the big contributors to the National Electric Code in general, and safety in the industry. So please take advantage of their articles. All right, I think we're at our question session. Mike, I probably went over a few minutes.
Yeah, well, I think we've only got a couple questions in right now. I'm sure we'll get more in a little bit. But there was one here around communications, and I think it's worth spending a little bit of time on this. So the question is about if the inverter loses communications, does the optimizer automatically go into safety C mode? And this is something that I see get confused a lot. And it's because some other manufacturers of optimizers actually require communication to a gateway or communication to the World Wide Web to operate. And in our world, you're going to communicate from the inverter in two directions. One's to the cloud or the World Wide Web. The second is toward the optimizers. And so those are different things. If you lose communication to the World Wide Web, the system will still operate, the system will run. If you lose communication between the inverter and the power optimizer, that's when the safety C mechanism comes in. So the inverter is communicating. You can think of it like what do we call it? A keep alive signal. And it's so the inverter is going to be communicating to the power optimizer on a regular interval, and it just tells it keep producing, keep producing, keep producing. If the inverter does not send that signal, as in if the inverter is off or if the inverter is told not to send a signal, that optimizer will no longer see the signal. It will fail safe into safety C mode. So I want to separate those two things. Communication to the World Wide Web and the monitoring is not required for the system to operate. But communication between the inverter and the optimizer, which is done over that DC power line, so it's a PLC, but it's over a DC line, that is required. And so I just want to clear that up.
Yep, that's great. Yeah, and just so people are aware too, part of the product certification is to comply with the loss of control signal. In our case, it's the loss of that PLC signal between the inverter and the optimizer. So it goes to a fail-safe state.
So that's one. Okay, this one is about access to the inverter and access to the DC shutoff switch. So what kind of things should they keep in mind? And I guess this will depend on what type of inverter they're using, HD Wave or standard, and what type of code, either NEC 2014 or 17. So I don't know if there's an easy way to kind of step through that, but what are the consideration on inverter placement with regard to codes and the type of inverter?
That's a good one. I forgot to go into a lot of detail on that. That is important, actually. So NEC 2014 doesn't say that the initiator has to be outside, but it just makes common sense that you would want the rapid shutdown initiator outside. So why would you ask a firefighter to run into a burning building and find an inverter in a garage somewhere and turn the switch? They're not going to do that. So the initiator, by practice, is typically required to be outside. It's just not required by the NEC code in 2014. So NEC 2017 clarified that and said needs to be outdoors. And I think it says on single and multifamily dwellings needs to be outdoors. So that is clarified. In our product, you will see that I'll call it the legacy single phase inverter, the only way to initiate that and put it in rapid shutdown right now is to turn the rotary disconnect. So you need to put the inverter outside if you want the initiation to be outside when you're using that model. If you want to put the model indoors, if you want to put the inverter indoors and you want to be able to activate it from the outside, you would use the HD wave inverter and then put an AC disconnect outside. Or perhaps if there's an outdoor panel, you could use the breaker in the panel and have it labeled appropriately.
Yeah, so, and for just to kind of keep on this subject for a little bit longer, we talk about automatic rapid shutdown and manual rapid shutdown. Those are kind of internal terms that we use. The manual requires a person to go and manually touch the inverter and turn something off on the inverter. This is something you want when you're looking at StoreEdge applications. It's something that we've been doing as standard under NEC 2014. Now that we're looking at more 2017 systems, you've got an automatic rapid shutdown, and that means that a person doesn't have to go and touch the inverter. So that's sort of the inverter will automatically go into rapid shutdown mode upon loss of AC. And so that's the implied part. What that gives you is the ability to have an external breaker, or you're pulling the meter. If you're disconnecting AC, then the inverter will automatically go into that rapid shutdown mode. So that's what that terminology means. And hopefully that'll help you kind of work through the details there. We are recording this. There have been a couple questions, and we will provide the slides afterwards. So we'll send you a survey afterwards and fill out the survey, and we will send the slides over. Jason, is SafeDC integrated into all optimizers?
Yes, as far as I'm aware. I can't think of any optimizers that's not integrated into. Mike, I think what we're saying since the product inception, so the first optimizers were hitting the market in 2007, I would say.
Yeah, as far as I know, it's been in ever since somebody drew with a dry erase marker on a whiteboard that having electronics next to the panel, we would want some type of control of the voltage. Now, whether we turned it off or turned it or made it 1 volt, I think some of the legacy of that is us going and talking to installers and finding out that if we turn this off, it actually makes it harder to commission. You don't know if everything's wired up correctly. So the idea was to send out 1 volt rather than 0, so that when you connect these in a series, now you're seeing 20 volts. You got around 20 panels, or around 20 volts. You got 20 panels, and that was feedback that we got from installers. So yeah, some form of SafeDC has been in the product ever since it was written up on a whiteboard, and then when we were talking to installers, that's where it kind of evolved into this 1 volt SafeDC mechanism. Okay, this is more of an application-specific one. And okay, so in this case, we're outside. We're installing the inverter outside, but it has a closet around it with a door.
Okay.
So, does that? That's a very specific. Do you kind of have a picture of what we're looking at? He's got a shed with a door, and the inverter's inside the shed. Is that? I guess 20.
Yeah, maybe it's considered outdoors, but it's not accessible because there's a door. I would say you need to take that one up with the local HJ. That I think that would be interpreted differently in different regions. I think the key is access. So speaking to NEC 2017, it says, that's a good question. I don't know if the word is actually outside or outdoors. I could look it up. But the key is it needs to be on the outside of the building so that the firefighters can access it. So I would assume that, if there's good signage and the door is not locked, big sign on the door that says rapid shutdown initiator in here, that may meet the local requirement. But then again, it may not. They may say, I want it, exposed on an outside surface. in which case you'd need to put an initiator on the outside of that shed or whatever we're talking about. So, but yeah, talk about it with a local building department.
Yeah, that's always your best bet. There's one code. Well, there are plenty of codes, but there's usually one code in place, like NEC 2014 or 17, and then there are thousands of interpretations. So, for things like this, I think Jason has the right take on it. Rapid shutdown configured by default or not on inverters. So maybe we could color this out a little bit.
So the goal is that they should all come default with rapid shutdown enabled. The catch is we can't control what happens to inventory once it leaves the factory. So we could say that everything that leaves the factory today, it's enabled by default. But that inverter could go, to a warehouse. It could be sitting in inventory somewhere. We have no idea when the inverter was made that you might be receiving. And so some of the older inverters still don't have, they didn't ship with it in default enabled mode. And so just to be safe, we're recommending that people check in the menu to make sure it's enabled.
Yeah, I think.
I mean, you can take that chance. You can take that chance if you want, but then if you have an old inverter, then it may not be enabled, and it's better to check it and just confirm that it's enabled than to not check it.
It's been about a year and a half that we've been shipping with it enabled by default. Does that sound about right?
Yeah, that's what I've heard.
So I mean, your odds are you're going to be getting it enabled by default. What we're talking about here is let's just check and make sure, so that you don't have you don't fail your inspection or something. It's just worth it to check, but 90% of the time, 99% of the time, you're going to be seeing that it's enabled by default. Okay, this one's ground fault. So can the safety C mode be misread as a ground fault? I'm going to expand that and say, or as an arc fault, because I was actually in Israel when we were going through this. Do you know the history with this, Jason?
Can the safety C be interpreted as a fault? Is that the question?
Yeah. So there's a story kind of to this. I don't know. This is a couple years ago that I was in headquarters, and so I had an opportunity to kind of be on the ground floor when they were going through this. But at the time, we were looking at arc fault, and we weren't looking at safety C. Safety C is pretty stable. We were looking at communications. So if you have everything connected up and the optimizers, trying to communicate telemetry data over the wires, is that going to be seen as an arc fault, or is that going to send a signal?
I see.
And that's one of the benefits of doing both sides of the puzzle. So if you're making optimizers and inverters, you've got the ability to plug them up together and start testing it from day one. And so we were able to come out with a solution. There are other optimizer companies out there, and they ran into a brick wall when it came to false triggers of arc faults. I don't know if ground faults were an issue there, but it wasn't the safety C. It was more the communications that was causing it. And so we were able to test it from day one. And because of that, we knew that we had to change our hardware. We actually had, a couple sets of hardware we were testing at the time, and we had to trim it down. And there were only a certain number of ways that we could test for arc fault. And we came up with one that was more reliable, more robust, and didn't give you all the false trips. And so we didn't run headlong into that brick wall. But that's kind of one of the benefits of developing both sides, the optimizer and the inverter, in the same lab with the same engineer, as opposed to trying to do this with two different companies and then trying to stitch it together in the field. You're much more likely to run into problems that way than having this be figured out in R&D, in the same room with the same engineers talking to each other face to face.
Yeah, that's good. It's good to know the history. I wasn't aware of the history on that. But I mean, what I can say for today is that those things are all very distinct features. So for example, ground faults have a very distinct signature, and so do arc faults, and those actually can be more complicated to detect than a safe DC heartbeat signal. And so when those types of things are connected, are detected, there's a very specific error code that comes up in the inverter. And the inverter knows it's an arc fault or it's a ground fault. That's a different thing than the communications signal. The communication signal is it's a very simple, we'll call it low fidelity signal that happens on the DC lines, and it's very simple. It's either, hey, am I there? Every couple of seconds. I don't remember how frequent it is, but it's just the inverter is literally pinging the optimizer to make sure the optimizer is pinging the inverter to make sure that the inverter is there. And so when that signal is lost, it just goes into safe DC. When a arc fault is detected or a ground fault is detected, it's a completely different sequence of events that happens. The result is the inverter goes into safe DC, but then to comply with UL 1999B, I'm sorry, 1699B, we have to do a lot of other things when an arc fault is detected. The same with ground fault. So they're separated out in the functionality of the system, and we don't really have a interaction between the different functions. Like, I haven't seen when the system's placed in rapid shutdown, I haven't seen like a false arc fault error occur or a ground fault error occur. So those are separately reported and errors.
So I've got two more. Well, I've got kind of one general subject, and then I think we're at a good stopping point, 15 minutes after the hour here. But a little bit about commercial, just to kind of touch on this. And, how do we meet rapid shutdown with three-phase inverters? Obviously we can put more modules on a string. So what are strategies to get below 30 volts when we can have 15,000 watts on a single string?
Yeah, so we have 2-to-1 optimizers for rooftops. That gets you to 60 modules per string, which is, I think, quite good for commercial rooftop. If you're going to build longer strings and you're on a ground mount, doesn't matter. You don't need rapid shutdown. Same goes for carports. But on a rooftop, yeah, you've got to keep the number of optimizers below 30 volts.
Yep, and so 2-to-1 is for commercial. Just so everyone knows the latest, we've got 2-to-1 optimizers for 60 cell, 72 cell, and now we have 2-to-1 optimizers for even the higher power 400 watt and below modules. So we've got two different variants of the P800 now, depending on what modules you're using. So, almost no matter what power class you're looking at, you've got an opportunity to go 2-to-1, which is going to not only lower your capital costs, but probably be a little quicker to install those. So it's a good opportunity to get your costs down, but it's going to help you with the rapid shutdown too, because now you're looking at cutting the number of power optimizers in half, and that's going to get your voltage down. So that's kind of how that's done. If you are looking at a 1-to-1 and you are trying to meet rapid shutdown, you will need to keep the number of optimizers below 30. But usually that's kind of a rare case. Most 480 volt systems installers are using 2-to-1, and they're going with P800, P700. P700 is by far the most widely used product that we ship, but the P800 is kind of new, so that'll probably start to take over very quickly. So if you are interested in commercial and want to set this up in rapid shutdown, look for the 2-to-1 and contact your sales reps around either the P800 or the P700. That'd be my advice on that.
Yeah, I'll add one thing to that. We were talking about locating the inverter on the rooftop near the array boundary, etc. I see our diagram here. We're assuming the inverters are mounted on the wall here. With the SolarEdge product, it really doesn't matter where you mount the inverter. You'll be compliant with rapid shutdown in any location. So you just can't put the initiator indoors, we'll say. So you could put it on the side of the building. That would limit your DC conductors to 30 volts outside of the array. So you could use 60 modules on the 2-to-1. If you needed to build longer strings, you could put that inverter within the 10-foot boundary for NEC 2014, because that would meet the requirement. For NEC 2017, you could put it within the 1-foot boundary and up under the array, because that inverter is listed for rapid shutdown functionality. You would just be restricted then to 80 volts, because you'd be within that boundary. So you could go, I don't know, conceivably with 80 optimizers. Now that probably violates one of the design rules for the system, but I think the key takeaway is you're flexible. There's no place that you have to put the inverter just to meet code. You can choose what makes most sense on the job site, what's most economical. What does the customer want? If you're in we've seen this in strip malls, for example, when there simply is no wall space, and all that wall space is used for some sort of a retail, advertisement or something. There's nowhere to put the inverter on the wall. So it either has to go indoors in a mechanical room, or it has to go up on the roof somewhere. So it can be compliant with rapid shutdown wherever you put the SolarEdge product. So.
All right. Well, thank you, Jason. Another great webinar for us, and I hope everybody has a great weekend. Get some jobs done, get some time with the family, and enjoy your time away from the office as much as you can. And thanks again, Jason, for your expert input here.
Thank you, Mike. It's always a pleasure.
All right. See you guys later, and on our next webinar, and hopefully you can join us again soon.